Hi, I'm Don Dooley, President of Spectrum Detector. We've created a brief video of one of our SXJ D products, model SXJ D 10, digital silicon jewel meter. Let's start by reviewing the features and performance of this product. It's a fully integrated device, includes a detector, integrating preamp, made it to a microprocessor-based digital electronics, includes a USB connector, which powers the electronics and acts as the virtual COM port. It includes a green LED power on light. It comes with a versatile standalone LabVIEW software and USB drivers. It can be set up as a single or dual channel instrument. Our application software supports both. It's the same software that supports our Delta product line. We offer this in several models, either with silicon, germanium, or pyroelectric detector. This is a very sensitive silicon digital jewel meter. It can measure on the low end down to 200 femtojoules, on the high end up to about 200 nanojoules, depending on the RV factor of the probe. You can measure from 193 nanometers up to about 1100 nanometers with this particular device. You can measure a single pulse up to about 1,000 pulses per second, and pulse widths from max of 10 microseconds down to something less than femtoseconds. All of the jewel meters include NIST traceable calibration and wavelength correction. Now let's take a closer look at the jewel meter probe hardware. It includes a front bezel with a removable aperture, a SM1 threaded hole here that allows you to add optical accessories like an ND filter by simply screwing it in place. It includes the detector module, has the detector, an integrating preamp, and the EEPROM, and that is connected to the back half of the instrument, which has the microprocessor based digital electronics and a USB connector for both power and the communication with the computer. And this is a green power on LED. Now let me walk you through the optical setup before we start the demonstration of the instrument and software. This is our SXJ D silicon digital jewel meter. I've added an ND2 filter to the front of it to make sure we don't saturate the photodiode. This is an ND filter wheel. This is a neodymium YELF laser head. That's 1.047 micron wavelength. This is our laser controller and oscilloscope, and of course our laptop PC. Let me show you how easy it is to set this up now. You connect this end of your USB cable to your PC, the other end to our instrument, at which time you'll see the green LED come on. That's powered up now, ready to go. We'll connect the analog BNC connector output to the scope, and now we're ready to bring the software up, and we'll assume that you've already downloaded software and you've got the software icon on your laptop. So double click on that. It comes up and says, well, it asks you first, did you indeed connect the probe? You say yes by clicking on proceed. It says wait here, which means it's going through its initialization process. Once the wait disappears, we'll be ready to turn data collection on and make a measurement. There you go, it's gone. So I click on data collection. You see we're now measuring about 15 nanojoules and displaying on the strip chart a 50 pulse data set in high resolution fashion. Now we're ready to take a close look at the SXI Delta LabVIEW application software. This is revision level AM. This is the control panel, which is always visible to the user. In the upper left hand corner is a large window where we display pulse energy in real time. We're reading about 87 microjoules right now. Just below that are 4 windows where we display the calculated statistical data set: min, max, mean, standard deviation. Up in this right hand corner is the data collection button. This is how you turn data collection on and off. Just below it is a log to file button to log data to a file on your computer, and this window actually shows the file we have open to which we log the data. Now moving below this area we get to a couple of the controls. This is a range switch, basically. You click on that and you can manually range the instrument from 2 microjoules to 20 millijoules for this particular DPJ joule meter. To the right of that is a trigger window. This allows the user to set the trigger anywhere from 2 to 20% of full scale. We're set at 5 right now. Moving down in the lower part of the display, there are annunciators, status annunciators here. There's a window that displays the RV of the probe in volts per joule. There's a wavelength window that displays the wavelength that we were measuring at, which is in nanometers, 1047. There's a trigger annunciator, which should be green if it's triggering properly. Just below that, there's a frequency and range annunciator, which should also be green. It means that we're within the 1 to 1500 hertz frequency range capability of this instrument. In the lower left-hand corner is a window that shows the actual frequency that the laser is running at. Right now, that's 20 hertz. Now let's move to the right underneath the strip chart. This is where the user will set the method of collecting data. You can, in this window here, it's called sample collection, you can set fixed or continuous. In the fixed mode, you're actually going to set a batch size. We've set a batch size of 50. You can reset that manually or use auto reset. Right now we're in the auto reset mode, so it will update every time it gets 50 pulses. There's also the continuous mode. When you click on that, it's going to measure every pulse until you stop it. The batch size no longer means anything. There's a collection mode, which is either streaming or time interval. Streaming is the way we're using it now. If you wanted to set a period of time to take data, that allows you to do that. Now let's look at the 4 screens that are available as part of the software. The first one is the strip chart. This is where we plot pulse energy per unit time. So we're looking right now at the 50 pulse data sets displayed in an auto scale mode, so it's maximizing the resolution. We're reading from 87 down to about 86 microjoules. You take auto scale off, now you're going to read about 87 microjoules on a scale of 0 to 200 microjoules. The next screen is a histogram. In this screen we're showing the data in pulse energy in bins. The user can actually set the bin size using this box up here. Tuning mode. This is a convenient analog tuning screen that allows you to tune the laser or peak your laser when you're setting things up. Here I'm putting an ND filter in the laser beam. You can see the readings changing and you can see the needle moving back and forth very rapidly. The blue needle is the minimum reading, the red needle is the maximum reading. And the actual readings are displayed to the side here. The next window is the setup window. Very important because this is where you, the user, set the wavelength at which you want to measure. This window here allows you to go in and set the wavelength. We're set at 1047 nanometers now. When you change the wavelength here, the wavelength correction factor changes. Right now it's 1. The window to the right of that is the transmissivity window. This is where you set the transmission loss factor basically for an attenuator if you're using an attenuator on the probe. The window next to that is the where you set the diameter of the sensor or the diameter of the laser beam. If you want to measure in joules per square centimeter, you then just click on this button and you can change the reading to fluence. There's also a very handy auto set button. It's like the auto set on an oscilloscope. When you're just setting things up initially, you can get your laser running, line the detector up, and then hit auto set. It will automatically look for the appropriate range and trigger level to start this instrument working. Well, that brings us to the end of our product demonstration. I hope you found it useful. Give us a call if you have any questions about this product or others.